So let's say that we wanted to do a test of homogeneity on this data set. Reminder, we're doing a test of homogeneity because the column totals are fixed. So let's just write out what the null and the alternative hypothesis are. So when we're doing a test of homogeneity, we're looking at whether the proportion is the same between the two groups. So the null hypothesis here is that the proportion or percentage who smoke is the same in the heart attack and non-heart attack groups. Okay. And our alternative hypothesis here is that the proportion is not the same. Between these two groups. Our test statistic is similar to what we've always done. We're going to do the observed minus the expected squared. So we're going to need to go through and work out what the expected is, right? So we've got our observed, those are all there, but we're going to need to go through and work out what the expected is. Okay. So a reminder, we do the row total times the column total divided by the total. We're missing the row totals here, so we better sort of go through and work that out. So 33 and 18 for that first row means that there's 51 total who are smokers in this study. And if I do 167 plus 182, that gives me 349 for total non-smokers, which is good because both of those numbers add nicely to give me 400. So I know I've done that correctly. So from there, I'm ready to go. If I want to work out the expected number here, I'm going to do the row total. So 51 times the column total, which is 200, divided by the 400. And that gives me 25.5. Okay. And then let's do this next one here. So this one here, I've got the row total. So 349 times the column total, 200 divided by the 400. So 349 times 200 divided by 400 gives me 174.5. And you could follow sort of the similar rules here to work out the expected values, and you're going to get 25.5 and 174.5. I hope it's not a surprise to you that these numbers would be the same. Remember here, this is the expected value given the assumption that the proportions are the same, right? So if there was 200 people in each group, these proportions should be the same. The number in each group would be the same. Okay. So we're ready to calculate out our test statistic. So it's our observed. So let's start with the first box. 33 minus our expected, 25.5 squared, divided by 25.5 plus the next box. Let's go over to the right. So we've got 18 minus 25.5 squared divided by 25.5 plus 167 minus 174 squared divided by 174. Oops, I forgot the 0.5. Silly little mistake, but it might matter here. There we go. And last but not least, 182 minus 174.5 squared divided by 174.5. And when I worked that all out, I got 5.05. Again, this is going to follow a chi-square distribution, and my degrees of freedom is always the number of rows, which is 2 minus 1, times the number of columns minus 1. So in this case, 1 times 1, which is 1. So if I wanted to draw a picture here to sort of represent what's going on, there's my chi-square distribution with 1 degree of freedom. I'm going to plot on 5.05. And this area here, that's my p-value. Okay. So I might go through and work out the actual p-value using R code. So I'm going to use P I want the probability chi-square, and then plug in the test statistic, the degrees of freedom, and then remember we need lower dot tail is equal to false to make sure that we get the area to the right. You can plug that into R yourself, and when you do, you'll get 0.025 if we round. Okay. So based on that, we're going to take this p-value, and it's definitely less than my alpha, which was the 0.05, which means that I'm going to reject H naught. If I reject H naught, that means I have significant evidence for the alternative hypothesis. So I'm going to conclude here there is significant evidence to suggest that the proportion who smoke is different between heart attack victims, patients, maybe I'll say patients, and those who have not had heart attacks. And quite often I like to present in my concluding statement the p-value, just so that people can judge on their own what the strength of the evidence is. So one thing just to point out here is that because these row column totals were fixed, it changes what the null and the alternative is and the type of conclusions that we're able to make. So this is maybe not as strong a statement as being able to say that there is an association between these two variables, but that's a limitation that we have based on the fact that these are fixed. Let me just walk you through maybe why that might be to our advantage sometimes. So for example, right, if we had fixed this 400 and made it a true observational study, the percentage of people who have heart attacks, if I were to survey the general population, I would think that would be quite small. I don't know the exact number, but let's say it's 1% or something, right? That would mean that we would expect sort of on average about 4 people here to fall into the yes heart attack out of the 400 and the remaining to fall into the no. If I only have 4 heart attack people, then it doesn't really get me a good idea of what this ratio here is or the proportion is who smoke, right? So the only solution to that is to make this sample size much, much, much larger, right? And so, you know, let's say it had been 4,000, then I would have had, let's say, about 400 here, and I'd get a better sense of that ratio. But maybe you don't have a budget to survey that many people, and you don't need to necessarily have, you know, that many not heart attack peoples to get a good sense of that ratio. So this is quite often done where they fix this, especially when one of these categories is rare or maybe much more probable than the other, or maybe we're just not interested in that ratio. This can help us to just get at the difference here, the difference of proportions, and that might be enough for the sake of the study that we're trying to do.